So today, we're going to dive into one of the most elegant and honestly powerful tools in all of physics, dimensional analysis. Think of it as a secret weapon, a way to understand the very structure of physical laws by checking if they even make sense before you ever pick up a calculator. Let's see how it works.
Right? How on earth is that even possible? How can you look at an equation that might describe how the universe works and decide if it's plausible without a single measurement? Well, the answer lies in understanding the fundamental nature of all the pieces involved.
Okay, so here's our game plan. First, we're going to nail down what we even mean by physical dimensions. Then we'll get into the single most important rule that governs them all. After that, we'll put that rule to work first to check equations we already have, and then, this is the really cool part, to actually build new ones. And finally, we'll talk about what this tool is great at and what it can't do.
So, first things first, what is a dimension? Now, I'm not talking about 3D space or anything like that. In physics, when we talk about dimensions, we're talking about the fundamental building blocks of, well, everything we can possibly measure.
This right here is the absolute key. It's all about the qualitative nature. A length is a length. You know, it doesn't matter if you measure it in meters or miles or even light years. The unit changes, sure, but the fundamental idea of length, that dimension, that stays the same. The dimension tells you what kind of thing you're measuring, not how much of it there is.
And what's so cool is that basically every physical quantity you can think of, velocity, force, energy, you name it, can be broken down into some combination of just these few base dimensions. Think of them like primary colors. The big three we'll be using most are mass, which we write as m, length, L, and time, t. Everything else is just a mix of these.
Now, it's also really important to make a distinction here. Some things, like velocity or force, have these physical dimensions. But other things like pi or the number 2 are just pure numbers. They're dimensionless. They don't have a physical nature. They're just scaling factors. And keeping that difference in mind is absolutely crucial for everything that comes next.
All right, let's get to the heart of it. This is the single most important rule in all of dimensional analysis. If those base dimensions are the alphabet of physics, then this principle, it's the grammar. It's the rule that tells us how to build meaningful sentences. And look, this isn't a suggestion. It's a hard and fast rule. For any equation in physics to be valid, the dimensions on the left side of the equal sign must be identical to the dimensions on the right. And, just as important, you can only add or subtract things that are the same kind of thing. Apples and apples, not apples and oranges.
And this analogy just nails it, right? I mean, this is something you already know intuitively. You can't add 5 kilograms to 10 seconds. The question itself is nonsense. This principle of homogeneity just takes that common sense idea and turns it into a super powerful mathematical tool.
Okay, so we've got this grammar rule. Let's see what it can actually do. The first major application is using it to check if a physics equation is, dimensionally consistent, if it's homogeneous.
We'll take a classic equation from kinematics, one you've probably seen 100 times. Final velocity equals initial velocity plus acceleration times time. Now, to see if this equation respects our grammar rule, we have to look at the dimensions of every single term.
Okay, first up, the left-hand side. We have final velocity. Well, what is velocity? It's a measure of how much length you cover in a certain amount of time. So its dimension is length divided by time, which we write as L times t to the power of -1. Simple enough.
Now for the other side of the equal sign. We've got two parts to check. The first term is initial velocity, which of course is still a velocity, so it has the same dimension, L t -1. The second term is acceleration times time. Now acceleration is a change in velocity over time, so its dimensions are length per time squared, or L t -2. When we multiply that by time, t, one of the time dimensions on the bottom cancels out, and what are we left with? Well, look at that, L t -1.
So let's step back and look at the whole thing. The left side is a velocity. The right side is a velocity plus another velocity. We are adding two things with the exact same dimension, and the result is a quantity with that same dimension. So, check. The equation is dimensionally homogeneous. It follows the grammar of physics. Okay, checking equations is one thing. That's useful. But this next part, this is where dimensional analysis goes from being a fact checker to being a tool for discovery. We can actually use it to figure out the basic form of an equation, sometimes without doing a single experiment. So here's the setup. Let's say we want to figure out what affects the time period of a pendulum. We can make a good guess that it probably depends on the mass of the bob, the length of the string, and the acceleration due to gravity, but we don't know how. So we just assign some unknown powers, A, B, and D, to each one. Then we just insist that the dimensions on both sides have to match up. That gives us a few simple algebra problems, one for each base dimension, and all we have to do is solve for our unknown powers.
And when you actually do the math and solve for those exponents, you find something that is just mind-blowing. The exponent for mass, A, turns out to be 0. And anything to the power of 0 is just 1, which means the mass term just vanishes. It's gone. Think about that for a second. Without touching a pendulum, just by demanding that the equation be grammatically correct, we've discovered a deep physical truth. The mass of a pendulum has absolutely no effect on how long it takes to swing. That is incredible.
Now, as amazing as all this is, we've got to be real. It's a powerful tool for sure, but it's not a magic wand. It's really important to understand both its strengths and its weaknesses.
First off, remember that constant in the pendulum equation? This method has no idea what that number is. It's blind to any dimensionless constants, like 2 pi. It also falls apart if the real formula has things like sine or cosine functions in it. And sometimes, completely different physical ideas, like work and torque, happen to have the same combination of m, l, and t, and this method can't tell them apart. But this last point is the biggest one. Just because an equation is dimensionally correct doesn't guarantee it's the right physical equation. It's a necessary first step, but it's not the final word.
And really, that's what it all comes down to, isn't it? Dimensional analysis is an absolutely brilliant filter. It lets us immediately throw out equations that are guaranteed to be wrong. It even helps us guess what the right ones might look like. But it only ever shows that an equation is possibly correct. The final step, the only way to prove that it's actually correct and truly describes our world, is and always will be through careful, rigorous experimentation.